Hello there, this is Toby. Welcome to part 2 of my introduction to the time traveling debugger. Time traveling debugger. Time traveling debugger. Yeah. So welcome to part 2 of the time traveling debugger, which I've been working on. And this time, the main thing I want to show you is the how it works with objects in the heap. So objects in the heap. This word heap, what does it mean? Well, for now, I'm just gonna hand wave over it, but the heap is a memory location similar to the stack frame. So in conventional programs, we have the stack and the heap. Both of them are a sort of these allocated memory areas, and we separate them. But in reality, both of them live in memory somewhere. The stack holds the stack frame, which has a number of frames, and the number of frames just sort of grows and shrinks as the needs of the program arises. That's the stack. The heap is for storing data structures that will be referenced by the stack, but they should not go away just because one frame gets destroyed. So they're for sort of like longer lived data structures. So stores long lived data structures, and which will at some point get referenced by the variables on the stack. Okay, and at present, for the fun programming language, which really in many design choices follows the design choices of JavaScript, and this is no exception here. In the fun programming language, the only data structures that are stored in the heap, I'll say data structures stored in heap for fun meaning funlang, those are arrays and dictionaries, also known as objects, because in reality they are objects in JavaScript. So only arrays and dictionaries belong into the heap, and objects and strings belong to the stack. That's how things work for funlang. Okay, so let me just show you one example program in action, and then I will explain more. So I have this collect multiples program, which will go through the numbers from 1 to 10. It'll collect the multiples of 3 into this array, which I called multiples. So go ahead and run that program. Play collect multiples fun. Okay, and now I'm going to use the debugger on this program. Okay, so now the moment I execute the first line, you can see that the value of multiple is actually a number, a 1, but it's not meant to represent a number because it's supposed to be an array, but this 1 is actually an ID which references an object in the heap of the same ID. So multiples equals 1 means multiples is an array which is basically the array in the heap with the ID 1, which at present is the empty array as is depicted here. Okay, and then now I is 1, and for I that's actually a number. Now whether we should have some sort of visual indicator that this is an array or a number. I think we definitely should have that, but this is a very experimental stage of this debugger, and at present I don't have anything to tell you whether this is an array or a number. Okay, anyway, so while I is less than 10, which at present it is, it'll do this if statement. Is it divisible by 3? No. It'll add 1 to I, and it'll do it again. And now it's divisible by 3. It'll push I into multiples, and now this array, the array number 1, will get the number 3 in it, and so forth. And it'll also get the number 6 in it, and it'll also get the number 9 in it. Okay. Now I want to explain, I chose to use this ID scheme for objects in the heap. By the way, this is the case for both arrays and dictionaries, as I mentioned. Actually, before I explain, I'm going to run one more example first, which would be the word tally. Yeah, let's run the word tally, which goes through, it counts words from this sentence, to be or not to be. This is my favorite programming exercise to give to my students. One of the favorites. Okay, so let's step through this line by line. So first we instantiate sentence to be the string, and then this split operation splits the string into an array of strings, which is depicted here. So this array has the ID of 1, and its members are these bits of strings that you can see here. And you can also see that the value of words has been set to 1, which is a reference to the array number 1 here. A tally is a dictionary, and a dictionary is depicted like this. Currently it's an empty dictionary, which is, for some reason, I chose to depict it like this. And again, the dictionary has an ID, it's 2, and the variable tally simply contains the ID to this object here in the heap. Okay, so now we're going to loop through the words, which again is array number 1. So we're looping through array number 1, and the first word in the array is 2. So right now word equates to 2, as we can see in the stack here. And then it's basically checking, hey, is the word 2 in the tally, which is dictionary number 2. And because it's not, it goes into the else clause, and it's going to set the, it is going to create a new entry for the word 2 and set the value to 1. So now we have an entry in this dictionary. It's no longer an empty dictionary. And move on to the next word, or, and wait, what happened to B? Oh, there's B. Oh, it went by too quickly. 2, and then 2, and then B. Okay, there's B. Why did it go by so quickly? Okay, B has 1, and then we go to OR, and OR has 1 as well. And then NOT has 1 as well. Now we get to 2, where we're actually going to get a repeat here. So because OR is already in the dictionary number 2, tally, it's actually going to add 1 to the existing number, which should get us 2. So you can see 2 in the entry for 2. That's a mouthful. Okay, so now, and then B is going to get another increment in the count as well. And that ends the program here. So that's what it looks like when you're working with arrays and dictionaries, both of them data structures in the heap. Now I want to explain why I chose to use this ID scheme for the objects in the heap. So the problem that I ran into as I was designing this thing is that Okay, let's say you had a function. Let's say you pass an array or a dictionary into a function, which I actually have example of this, or perhaps I modify this example to maybe I extract these 3 lines from this collecting multiples example, and I make that into a subprocedure. I'll say collect. I'll say maybe collect multiple of 3, and it gets passed in the array here, and also the I. So instead of doing these 3 lines directly, I'll actually pass in the I and the array. And if I ran this, it should do exactly the same thing. Let me double check that I did this correctly. So now if I run the debugger on it, so I have another frame in the stack frame here, and the multiples within this frame is also pointing to 1. So both the multiples variable in main and the multiples variable in maybe collect multiple of 3, they're both pointing to the array 1. And it also has an I, so it's testing I. By the time we get to the I equal to 3, it'll go into this if conditional, and it'll push the number into the array as it did here. So this works perfectly as it did before, and we should get 3, 6, and 9 with more steps than before because we had this function call to deal with. So in order to get all of this work, I had this problem of, so if I have, because I need to store all historical states and using of the entire program using the immutable data structures scheme, I can't actually be modifying data structures even when I'm modifying data structures. So in other words, this push operation here, it cannot actually be modifying a data structure. This push can't mutate the array in reality. Instead, what it has to do is to create a new version of this array. The problem is if I create a new version of the array, I need to notify all references to that array that the version of the array has changed. So, and that is a problem when anytime you have multiple references to that same array. So for example, in this case, actually, this already happens whenever, I'll just go back to the first time it's going to push a number. Yeah, here. When here happens, we already have 2 references to the same array. So so here we have this situation where we have 2 stack frames, and yes, we have this 1 here, but without my numbering scheme, then this would actually, let's pretend this 1 was not here. This would actually be a pointer to this array, and this would be a pointer to this array as well. And if we're going to say we're doing this immutable sort of modification of the array, which means I have to make a new version of this array with the 3 in it, and I'm gonna make this multiples variable not point to the empty one, but make it so like sort of erase this, but make it point to the new one instead. Well, that's not gonna work because I also have to modify the outside reference to the same array, because the main function is expecting the sub function to be mutating the same array that the main function is expecting to be able to access later. So in reality, this scheme basically doesn't work, because anytime we modify this array, we have to make sure, and which means creating a new version of the array, we have to make sure all of the existing references to that array have to get updated to refer to the new version of the array. I thought of multiple ways of doing this, and at the end I decided the simplest way, although less performant way, is to come up with these ID scheme. And this ID scheme allows us to sort of at a global level for all of the variables within the entire stack, and also in fact not just the stack, but you can have arrays of arrays as well. So if you have arrays of arrays of dictionaries, or dictionaries of arrays, the members of the array is also IDs to other arrays. So these are in fact IDs to other arrays if you choose to do an array of array approach. And in those cases, when you're mutating things, things will continue to work as well. So now I want to show you how the heap is represented inside the history file. So this history file is for this collect multiples program. You can see that initially the heap is empty. It's just represented by an empty object. This object is supposed to be a dictionary where its key is the object IDs, and the value is the actual object. So when we executed line number 2, which is this line, and instantiated an empty array, what happened is we created a new object in the heap and gave it an ID of 1, and the value of the object is, as you can see, an empty array. And then the multiples variable in the stack has the value of 1, which is basically an ID that points to this entry in the heap. So that's how it works. And anytime an object inside the heap has to change, basically the value in the entry gets changed. However, that doesn't affect the previous version of the historical version of the heap, because this version of the heap, this state of the heap, has an empty array, and nothing will change that. So when the heap actually changes, as was the case, where did the heap actually change? There. Okay. So here, this happened after line 12, which was here. Yeah, that makes sense, because after line 12 is the line that pushes a number into this array here. So after line 12, we see that the array number 1 in the heap has a 3 in it now, and that's how the heap changes. Because but the fact that the state of the heap has a non-empty array in it here doesn't change that the previous state of the heap was an empty array. And then also, because the references to the objects in the heap are simply numbers, the references they're sort of decoupled from the actual content of the heap, and the heap a heap lookup is done at runtime. So whenever the program actually tries to get at the actual array, it just uses this ID to look up this heap, and everything just works out like that. We can look at another example. We can look at the word tally example. So word tally has a history file, and you can see that the heap, let's see, at the beginning the heap is empty, and then here the heap has an array. This is the result of splitting the sentence into words. So this is the words array, ID1, and that points to this array with all the words in it. And then we're gonna loop through, and here we generated the tally variable, which is a dictionary, which is pointing to heap object number 2, which is here, and initially that's the empty dictionary, but over time this dictionary gets entries in it as we loop through the words, etc., etc., and this dictionary builds up. But the fact that this dictionary gets new entries over time doesn't sort of, because we're not mutating anything, we still get to retain the previous states of the history in this history file, and that's what I was mostly after. So that's how this scheme works. So although this way seems like indirect and also it's less performant, I chose this way because it solves a whole lot of problems. And the performance penalty hit is something that I'm thinking about, and I think it can be mitigated in the case when we have pure functions, as in pure functions don't need this because pure functions are not gonna mutate anything. And so we can do an optimization there to not have to do this ID scheme in the case of pure functions. And also perhaps I feel like this ID scheme, although there is a penalty hit involved, maybe it's not so much. It's just an extra lookup. It's not so much that it'll be prohibitive for real world tasks, perhaps. And I guess only time will tell about that one. Okay, so that's how things work. And I think in a perhaps another video I will actually show more of the internals of how the history file and the snapshots within it are actually generated. And yeah, if you're interested in seeing more, then stay tuned.